I'll begin with a word of prayer. So, again, Heavenly Father, we thank you for this day. Thank you for tests, because they're so much fun. And I thank you for these students. Help us to, again, glorify you, what we do, as we study your creation. Give us understanding, Lord. In your name I pray. Amen. Okay, so I sketched for you guys this thing called the heat equation, right? And I want to solve one of those. And then hopefully time will permit me at least starting the discussion of the wave equation today, all right? So, heat equation. Solve a problem here. So this is actually, I have the solution written out in my in the linked solution, page 135 to 144, my practice homework solutions. There's a link to a PDF with what I'm about to go through in the course planner. But I probably will diverge from the line by line there, so you should still take notes, you know. Okay, so here's the problem. We're supposed to solve partial u, partial t, equal to 3 partial squared u, partial x squared, subject the boundary values. So boundary values here is going to be partial u, partial x at 0 pi, 0 t, I'll get it right here eventually, is equal to 0, and partial u, partial x at, let's see here, pi t is equal to 0. So you got these two boundary values, boundary conditions we have to fit rather, and this is for t greater than 0. And also, we have to fit the following initial temperature distribution. So the initial temperature distribution here is going to be u of x comma 0 equals to x for 0 less than x less than pi. All right, so we want to find a solution to this heat equation with boundary value problems. This is section 10.5, number 3, in case you're keeping score where I got this from. All right, what I want to do is I just want to go through the technique that we sketched last time and actually solve this one. All right. So let's see, let's go back. So what we do at the start is we propose that u of xt equals to x of x, t of t, right? And so uxx equals to x prime prime t, and the partial derivative with respect to time gives us xt prime. Plug those into the differential equation, we get what? We get x t prime equals to 3. Let's see here, 3 x prime prime t. Now take that, divide by the solution, xt, and that will give us that t prime. And I'll put the 3 over here, over 3t is equal to x prime prime over x. Now, at this point we made the observation, okay, on the left-hand side we have a function of time. On the right-hand side we have a function of x. Consequently, this must be a constant. And for the purpose of syncing up with the propositions at the start of my notes, I'm going to call this minus k. All right, so then basically need to solve. We need to solve, let's see here, x prime prime plus kx equals to 0, and t prime plus 3kt equals to 0. All right, so without further ado, we can solve the second one of those, right? Second one of those easily solved. Pick your favorite technique: integrating factor, separation of variables, characteristic equation with operator factoring, like whatever you want. I like the last thing I said. So I'll just say, aha, well this says that lambda plus 3k equals to 0. So therefore lambda is minus 3k. And so I find that my time, the time part of the product solution is just e to the minus 3k little t. All right. Thus, u, and we'll say, I'm going to say, well, anyway, u of x comma t is something like x of x times e to the minus 3 big kt, right? Apparently. I mean, that's a typical product solution. And so what happens if we feed our boundary values into that? Well, I guess I need to differentiate it this time, don't I? What happens if we differentiate this with respect to time? What's partial u partial x at xt equal to? Just x prime of x, right? Not especially exciting. What happens then if we feed the boundary values into this thing here? So we have partial u, partial x at 0t, right? Which would be x prime of 0 times e to the minus 3kt. And we also have partial u, partial x, pi t, x prime of pi, e to the minus 3kt, right? So I'm considering the boundary values. I mean, the boundary I should really call these boundary conditions, BCs. The totality of the problem is the boundary value problem. These are the boundary conditions. Yeah. Anyway, the exponential, of course, now this is at equal to 0, right? Equal to 0. That was part of the problem statement. And so this means then that x prime of 0 is 0, x prime of pi is 0. Aha, so actually we face the spatial boundary value problem of x prime prime plus kx equals to 0 subject the homogeneous boundary conditions x prime of 0 equals to x prime of pi equals to 0. Again, in my notes that I've typed for you guys, I take some time to work out a few standard spatial boundary values. In particular, at the start of, let me remind myself what the name of that chapter is. So many pages to page down. I'll get to it eventually. Chapter 8, yes. At the start of my chapter 8, if you go and look at proposition 8.3.2, it actually tells you the answer to this spatial boundary value problem. All right. Now, so as a point of reference, you could use that. I think it's helpful for us to just focus on the interesting case here. So I'm actually going to do some of the details. So it turns out, observe, well, k equals 0 actually gives us something interesting this time, right? If you look at k equals to 0, we have x prime prime equal to 0. Therefore, x of x is what? It's ax plus b, right? If you think about that, can you solve both of the derivatives being 0 at 0 and pi and still not have a 0 solution? What would you do? The question I'm currently asking you would have been a reasonable question in like Calculus 1. Maybe it's an unfamiliar question, but it's a question you ought to be able to answer. If I want this and that to be 0, what do? I just make, I mean, what is x prime of x? It's just a, right? So if I make a equal to 0, b is free. So we could say that x sub naught of x could just be 1, right? The constant function 1 solves. K equals 0 actually does something interesting here. Now, k less than 0, not interesting. As it happens, you get cosh and sinh, right? And the cosh and sinh are going to be forced to be both 0 by the boundary values. Okay? So we'll look at the interesting case, but k equals to beta squared for beta positive gives us x of x equals to a cosine beta x plus b sine beta x, right? And what happens when you differentiate that? X prime of x is what? It's minus a beta sine beta x plus b beta cosine beta x, right? So evaluate at x equals to 0 and pi. What do we get? We get x prime of 0 is what? Well, the sine of 0 is 0, so that gives us b beta equals to 0, right? Because cosine of 0 is 1 and sine of 0 is 0, we just end up with a condition b beta is 1. Beta is assumed to be positive, right? So that tells me that my b has to be 0. But on the other hand, the pi is going to be more interesting. X prime of pi, well, that's going to be minus a beta, the sine of beta pi equal to 0, right? Again, the b term is already gone. Now, we don't want to have, if we have a equal to 0, that's not especially interesting, right? So we want a to be non-zero. If a is non-zero, we must have that sine, sine of beta pi is 0. And as we discussed last time, this implies that beta pi is equal to n pi for some whole number n, some natural number n. Therefore, my k, which was what? By construction, beta squared, is actually equal to n squared pi squared here. Oh, I'm sorry. I cancel the pi's. Beta's n, right? Sorry, I think I can afford one more line here, right? Therefore, beta is n. Hence, k is n squared. All right? And so we find not one solution, but a whole countable family of solutions, like one for each n. And so let's kind of summarize what we have then. Thus, u sub n. Let's see here how to say this. U sub n of xt is, let's see here, what term did we keep? The a one, right? Which was cosine. So we've got something like cosine and beta was n, right? So it's cosine nx times e to the, what was it? The time solution was what? It was e to the minus 3 kt, which in retrospect is e to the minus 3 n squared t, right? Or we also have that n equals 0 solution, which is just what? 1 times e to the 0. So the n equals 0 solution is kind of boring. It's just the constant solution, but there it is, right? There's infinitely many solutions to the heat equation which satisfy the boundary conditions, right? We haven't yet dealt with x, the initial condition, right? So this suggests then what I call the blank template. So it solves the boundary conditions, but not, well, let's say, and we hope the initial condition after appropriate coefficient selection. So what is that? We have u of xt is equal to 1. I guess I could, well, I should take weighted sums, right? So I should have something like, oh, I don't know what to say here. Let's say c sub naught plus the sum n equals 1 to infinity of my u sub n's. So I got something like c sub n cosine nx e to the minus 3n squared t, right? So we're adding together solutions which satisfy the boundary conditions. Boundary conditions are homogeneous, which means that the sum of solutions is still a solution which satisfies these homogeneous boundary conditions. You see, if I had non-homogeneous boundary conditions, I'd have to think harder about that. But they're homogeneous, so adding them together doesn't violate these things still being true, if you think about it. All right, so how do we choose the c sub n's? So here's my blank template. All right. In some sense, we're like halfway done at this point. I think of myself as, I think of this as the halfway point, right? See, I still have not yet dealt with this guy. Right now I have to think about how do I make that happen. So what I want is I want that u of, what was it? x0 is equal to c sub naught, right? Plus the sum n equals 1 to infinity of c sub n, the cosine of nx, right? You notice that e to the 0, this piece just drops to 1 down here because we have t times 0, right? It's important to actually think through that. There's another calculation we do in like the Laplace, like solving Laplace's equation, where that step actually, it can happen. There are problems where the structure of the problem actually brings in an influence from the time solution into the selection of the spatial coefficients. Like it doesn't have to be a non-event here. It's important to think through it. Okay, anyway, now we want this to be equal to what? X, right? And so this is going to be equal to, we want to construct x as a Fourier cosine series. So we want to construct Fourier cosine series. Now we could go through integration like we did last time and talk about how certain integrals are 0 and all that good stuff, but I'm going to be lazy. It's funny. I was laughing because of the way he had the book. And if we look in section 10 point, I think 10.4, 10.3. 10.4, yeah. He tells us that the Fourier cosine series, there's straightforward formulas for how to do this. Think of it in some sense as it's much like finding the Taylor series for a function. There's a set method to do that. So here we go. It's a sub naught over 2 plus the sum n equals 1 to infinity of the a sub n, the cosine of n pi x over t, as he calls it. This is so 0 to pi. So in other words, my t is pi in the formulas from section 10.4. So, this is really just going to be what? Cosine nx, right? The pi's cancel. And he tells us that the formula for the Fourier coefficient, a sub n, it's equal to 2 over t. Here t is pi. The integral from 0 to pi of f of x, in which in this case is x, cosine of nx dx. So here I'm identifying t equals to pi, f of x equals to x for our problem. So if we can calculate these if I put it there, you're not going to forget, are you? Okay. We just have to. So quite clearly, if you believe in math not being mean to you, it should be fairly clear that we're just going to set c sub n equal to a sub n for n equals to 1, 2, right? And what's my c sub naught going to be equal to? It's going to be a sub naught divided by 2, right? So let's calculate. Let's find it. What is a sub naught equal to? 2 over pi, right? Integral from 0 to pi, x dx, which is what? Come on, this one we can do. 1 over pi, x squared, evaluated from 0 to pi, also known as, see the 2's canceled, right? Integration gives me a half, but there's a 2 already there. They cancel, leaving me the 1 over pi. I get pi squared over pi. I get pi. My a sub naught is pi. So by comparison, we see that the c sub naught is going to be what? It's going to be pi over 2. There, one coefficient down, infinitely more to go. Right? But fortunately, the rest are the same pattern, right? We just have to integrate. We actually have to do this integral, right? How do you do this integral? You're like, well, you told me I can use Wolfram alpha, so I'm going to use Wolfram alpha to do that integral. Fine. So lazy. You're like, I'm not lazy, you're just a Luddite. Fine, you got me there. I do have a certain fear of technology. Let's see here. So this would be dv, this would be my u, right? Integration by parts will do it here. So that is going to be 2 over pi, and I get the integral of cosine is actually sine. So I get, looks to me like x sine of nx over n, right? And then minus the integral of sine of nx dx over n from 0 to pi, evaluated from 0 to pi. So you got sine of either pi or 0. So this first piece is gone. And we're left with minus, well, the integral of sine is minus cosine, right? So minus minus gives me a plus. I get 2 cosine n pi divided by n squared, because there's a pi also, pi n squared. See, the integration of sine brings out a 1 over n again, and antiderivative of sine is minus 1 over n cosine nx, that n squared and sec n squared. This evaluates from 0 to pi, and it's kind of a lot like the one we looked at last time. So this is 2 over pi n squared, right? And we got cosine, how did I do that? That's an x. I got cosine n pi here, I'm an idiot. It's cosine nx, right? Duh. Sorry about that. Anyway, so when you evaluate, we get cosine n pi minus cosine of 0, which is 1, right? Again, cosine of n pi is what? It's minus 1 to the n. So if you look at this, if n is even, then it's 0, right? So like n equals to, let's see here, n equals to 2, I would have 1 minus 1 is 0. So I basically am only going to have 2 over pi times 2k plus 1 quantity squared. Oh, and this becomes a 2. So I could just say 4 over 2k plus 1 for k equals to 1, 2, and 0 if n is equal to 2k. Well, let's just say n equals to 2, 4, and so forth. I'm out of board space here, but so in other words, after some calculation, I find that my c sub n is actually equal to a sub n. It's equal to 4 over pi times 2k plus 1 quantity squared for n equals to 2k plus 1, and also a sub 2k is equal to 0 for k equals to 1, 2, and so forth. Now we put it all together. Put it all together, and that gives us the solution. Therefore, we have u of xt. I had pi over 2 to start with, and then plus the sum. I'll put it in terms of k. K equals, well, let's say 0 to infinity. 4 over pi times 2k plus 1 squared. The cosine of 2k plus 1 times x, then e to the minus what? E to the minus 3n squared, right? E to the minus 3, my n is 2k plus 1, t. And there you go. That is the solution to the wave equation. The book probably would say formal. And the reason it would say that is because we haven't really proved that this series converges to the solution. So in that sense, it's formal. I have not the patience to prove this converges to the solution for you guys. Sorry about that. I had like a once-a-week meeting with like a couple students last fall, I think. We worked through a book by Haberman, which is just on partial differential equations. In that book, he actually develops theorems for like term-by-term differentiation of Fourier series and all that sort of thing. Some really weird stuff happens here, guys, by the way. Like, you can take a Fourier series which converges and differentiate it, and then the derivative will not converge. That's a little bit troubling. And actually, the difficulties, the subtleties involving Fourier series is what gave birth to a lot of analysis that mathematicians study to this day. The subtleties and what goes wrong in these calculations, it is subtle. And but Fourier just said, you can do it, right? And he had kind of a positive attitude and didn't belabor in the examples which blew up in our face and just kind of use physical to intuition or whatever, just keep on the straight and narrow. And that's the Wild West of mathematics, I suppose. Anyway, so there you go. Now, physically speaking, what we're looking at is, some rod that goes from x equals to 0 to x equals to pi. I think I called that L in our last discussion, right? And the boundary conditions here say that the derivatives are 0 at each endpoint, right? That means that these are insulated. So like it's an insulated metal rod, right? And the initial temperature distribution, it's temperature 0 at x equal to 0, and it's temperature pi on the other side, right? That doesn't violate the boundary conditions because this isn't the ice bath anymore, right? So here's like, u of x comma 0 equals to x. So it's like it's cold. It's kind of hot over here, right? And then what happens, does our solution make sense if you think about it? What happens as time goes to infinity in the solution? Only one term in our solution survives. Right? Time going to infinity, these become e to the minus infinity, otherwise known as 0, right? All these terms, gone. What's left? This guy. So it says asymptotically, since it's perfectly insulated, the temperature levels out at pi over 2 the whole thing, which makes perfect sense because the thermal energy can't flow out of the rod. It just levels out after a long time. In contrast, the ice bath problem we looked at last time goes to temperature 0 because all the heat flows out to the ice baths eventually, right? But makes a lot of sense if you start thinking about it, as long as you did the math right, Anyway, let's see here. How can I make this problem easier? So you guys asked me if there were 3 problems on the project, or how many problems there were, and I was a little bit of ambivalent. I was a little bit like, well, there's at least 3, right? One of the reasons for that is, I don't see myself giving like 6 of these kinds of problems, right? I don't want to look at that either, right? Come on. I want to get on with my summer. I got papers to write, you guys. Let's see here. Papers to write. Anyway, doing math is very fun. Writing up math is not fun. Let's see here. How can I make this way easier? What if instead of everything the same, right? But I say that u of x0 is equal to, I don't know. Let me think about this for a second. How about like 3 plus the cosine of 7x minus the cosine of 11x. See, at first glance, what I wrote in purple seems like a harder problem. 3 terms instead of 1 term, right? But no, this is a simple problem. Once you get to the blank template solution, you're done. See, because you can go straight from the blank template, look at this, and go, aha! Comparing to our blank template, you can just read from it, my C0 is 3, my C7 is apparently 1, and my C11 is minus 1. And all others are 0. So the solution is this. Now I got to be careful. How does the exponential work? It's e to the minus 3n squared t, right? This is going to hurt a little. N is 7. So n squared is 49. 3 times 49, 147. So e to the minus 147 t. Yeah. And what have I done? Minus cosine of 11x. 11 squared is 121. 121 times 3. 363? I don't know. Yeah, 363. So minus 363 time. There you go. See, a comparison of a blank template solution is not so bad, right? To my taste, it's when you have to do the full Fourier expansion that, to me, that's I mean, this is very benign, right? Like there are problems where this is more involved. Anyway, okay, so there you go. That's a full, honest to goodness heat equation with follow-up easy problems. So that's I feel like I have done my due diligence for the heat equation. Let's move on. Any questions? All right. There you go, some state-of-the-art theoretical physics from about 1805. All right. I guess I should probably should start over here. I hope you got this right. Okay. It's a little late to ask, but so, wave equation. What do you think the wave equation's about? Wave, yeah, waves, good guess. So in particular, it's about transverse waves. So something like this, you've got some sort of like string, right? And maybe it's stuck between two, so you can talk about fixed endpoints, x equals to 0, x equals to L, right? And we can just, for the sake of discussion, suppose that the string is fixed at these two endpoints, all right? And then you can, if you look at how the string is, it's pretty taut, thinking of it being pretty taut. And then as you know, if you pluck it or something, then your disturbance will propagate and make waves and so forth, right? And the wave equation describes that. In particular, we got to pick like a particular point on this thing. So here we would be at the point x comma u of, well, I guess I should say y. I guess to be more precise, it's really x at time t, y at x at time t. I don't know, something like that. Anyway, the point is, just to draw the coordinate system, y is like this, x is like that, okay? So y is the transverse direction, x is the direction along which the string is stretched. And so what we do to derive the wave equation is just pick a particular point, right? And just kind of zoom in on that. Let's blow that up. So you blow that up. All right. So we're basically going to ignore gravity. And so the primary thing what makes a string have waves on it? What would make a string not have waves on it? Like, what if you just took a sort of a string line on the ground or something and you just give it a wiggle? Pretty much nothing's going to happen, right? If the string is not taut, it doesn't have tension, there's not going to be any kind of interesting behavior. So it's not gravity that matters, it's the tension that matters. So we're going to ignore gravity and look at this little segment right here. And so what I'm going to say is suppose that has a mass, a little mass, which is basically given by the lambda times delta x. So here, lambda is going to be the mass per unit length, dmds if you like, the mass per unit arc length. So we look at this little segment of string, and then if you look at that, so there's tension, right? And the tension, we're assuming the string doesn't stretch. So like the magnitude of the tension would be the same on both sides, all right? Now my picture isn't entirely right, see, because the slope of the tension could be different on the one side and the other. So this point here would be x plus delta x, and then y plus delta y, whereas this point over here is just, let's say, x comma y, right? So the slope, so I'm basically making a free body diagram for this little segment of string. So I have the tension force to the right, tension force to the left. Now the direction, what's the slope here of the tension force? So here, the slope would be partial y, partial x at xy, right? The slope over here would be what? Partial y, partial x at what? At x plus delta x, comma, y plus delta y, you know? So we can look at Newton's second law in the y direction, right? And what's that give us? Mass times acceleration should be the net force in the y direction, right? And so let's see here. That's actually going to be lambda delta x partial squared y partial t squared, right? And to get the y component, if you think about this, right? If the slope is that, then if I do the slope times the magnitude, right? Slope times the magnitude should give me the y component of the tension, right? So over here, if I do t times partial y, partial x at x plus delta x, y plus delta y, and then I subtract t times partial y, partial, why do I subtract the other one? Because it's pointing in the other direction, right? So I'm taking t to be a positive thing. It's the magnitude of the tension in the string. Okay, so we have then is we have partial squared y partial t squared equals to t, let's see here. I guess I can keep the lambda over here. Lambda over t yeah. Just a second, I'll make a decision. Oh, fine, I'll leave the t over here. I don't know, I never can decide where to keep my t and my lambda. I'll put it over here, t lambda, and divide both sides by delta x. So here we got partial y, partial x, x plus delta x, y plus delta y, minus partial y, partial x, at x comma y, all divided by delta x, right? So what happens as delta x goes to 0? I mean, look at this. What is this? We're taking the change in the derivative with respect to x with respect to x. That is the second derivative with respect to x, is what that is. As delta x goes to 0, that's the second partial derivative with respect to x, right? So in short, we have this equation, partial squared y partial t squared is equal to t over lambda partial squared y partial x squared. This is the wave equation. Let's see here. I think I prefer to solve that for the x derivative, partial squared y partial x squared equal to 1 over lambda over t, partial squared y partial t squared. Well, like, that's great. Why did you do that? Did I do it correctly, I guess is the other question. Thinking I have it flipped. All right, you guys, what should I put in the denominator here if I could do algebra? Lambda over t, yeah, I think so. Let me just think about it for a second. I don't know. You notice I'm solving for this, right? So then when I put that over there, I would divide by t. You know, I'd have a lambda upstairs to start with. So if I bring it down in here, it's like that. I'm pretty. Hey, let's do a dimensional analysis right quick. You guys remember dimensional analysis, right? Tension is a force, right? You have kilogram meters per second squared, right? Lambda is mass per unit length, right? So that's meters, assuming kilograms over meters. So we're looking at kilogram meters over second squared over kilograms over meters for this thing here, which would give us what? Kilograms cancel. We get meters squared over second squared. Does that make sense that that kind of quantity would be there? Well, let's see here. So time squared has a second squared. You know, and so the times the second squared and the time derivative would cancel, and then you've got meters squared. You also have a meter squared for the y second, you know, partial squared y up here. So in total, that's dimensionless. Just like over here, I have second. I'm dividing by x 2 times, and I have y upstairs. Oh man, but I should have a. I shouldn't have dimensionless. I should have a. It should be like 1 over meters on both sides. Oh, it's because I forgot. I got a meter squared down here. I've only got a meter upstairs. So I've both sides, if I do dimensional analysis, I should end up with 1 over length after the dust settles. Anyway, they're dimensionally consistent, so we did the algebra right, whatever. All right, anyway, the larger point, oh, I shouldn't have erased that, is the units of t over lambda is meters squared over second squared. What does that suggest that t over lambda is? Units of length squared over time squared. So this is a velocity squared. V squared is t over lambda, or if you want to keep it positive, the speed, v, is the square root of t over lambda. So the speed of this transverse wave is the square root of the tension divided by the mass density. Does that make sense? I think that makes sense. If you stretch the string tighter and tighter and tighter, the wave will go across it faster, right? If you think about like a really heavy chain and think about like trying to make a wave in a chain, it kind of slowly propagates, right? Or maybe a heavy cable is a better thing to talk about. On the other hand, if you've got like a kite string and you just thwack it, you know, it'll go pretty fast. On the other hand, this means the heavier, you know, mass per unit length the string is, the slower the wave. That also makes sense with my intuition. Okay, so there it is. This is the wave equation. Can we solve it? So I'm just motivating at the moment. Now we've got a problem. So typical problem looks like what? We want to solve partial squared y partial x squared equals to, you know, 1 over v squared partial squared y partial t squared with boundary conditions. We'll use the fixed endpoint for the sake of discussion. Y of, let's see here, 0, comma t equal to 0, y of L, comma t equal to 0 for t greater than 0. And then we also need initial conditions. This time initial conditions because this is a second order. Interesting. I've grown accustomed that when somebody's staring in the window from the room, it makes me think that the room has been double scheduled, and they're like coming to tell me that because that's happened to me. Like my favorite double scheduling was the final exam last fall for differential equations. I get to the room, it's full of people. I'm like, what? What's going on here? It's a graduate biology intensive. He assures me that they have scheduled the room. I'm like, we usually have the final exam in the same room as the class for the whole semester, so I assure you this is where I'm supposed to be. So anyway, he graciously unlocked the biology lab, and my 6 students took their final for differential equations in a biology lab. It's very exciting. Anyway. Oh yeah, initial conditions. So sorry about that. As you know, I'm easily distracted. That has been established. Let's see here. So we'd need 2 things. We'd need, initial position and also initial velocity. So you need an f of x and a g of x. In other words, how the string is initially situated and also how it's initially moving. Both of those things would influence the resulting shape of the wave after that point. But here you go. This is the typical wave equation with fixed endpoints, right? How do you solve it? If you've really followed, like carefully followed the idea of what we did with the heat equation, you probably can already do it. So what's my opening move going to be? Suppose y of xt equals to what? How about x of x times t of t? So suppose you can form solutions by a product solution. Plug that thing in. What's it give us? From the second x derivative, we get x prime prime t equals to 1 over v squared xt prime prime. Well, this one's a little more fun, right? Because we got second derivative in time, the time function, and a second derivative in the spatial function. But you notice we can solve that. That gives us x prime prime over x equals to t prime prime over v squared t, right? This is like deja vu all over again. Function of x on the left-hand side, function of just time on the right-hand side. V is a fixed but arbitrary constant described by the tension and the mass density of the string. So that's just a number for a given problem. Oftentimes I make it 1. Anyway, so this should be equal to minus k because, well, again, I want to use my proposition 8.31 or 8.32. And if I do that, you see, this gives me 2 things to solve, right? It gives me x prime prime plus kx equals to 0, and t prime prime plus k v squared t equal to 0. Now I got a pair of ODEs to solve, right? And hopefully there's enough structure there, there's enough data there to construct the solution of the wave equation. In fact, there is. If you're looking for like a radically different third chapter to this story, when we go to solve Laplace's equation, I got bad news for you. It's going to be this same technique again. It begs the question. So like this idea of forming solutions by product solutions, what's the generality of? To what extent does it apply in general? Are there PDEs which this doesn't solve? I had no idea. You know, the problem of solving arbitrary partial differential equations is an interesting and open, active area of research. People have spent their entire career trying to give an answer to the question I just posed. To what extent does separation of variables work? I don't think that's known. People know a lot about it, but the end of it, no. Okay, so as before, our boundary conditions convert to x of 0 being 0, x of L being 0, right? And so by proposition 8.31, just to keep it simple, we're going to have that x sub n of x is equal to the sine of n pi x over L, right? Where we learn, or we find k is, what is it? I've forgotten my proposition. I better remember. We're almost out of time. If we had more time, I'd work through this again, guys. But it should start to be a familiar story. We'd have to consider the three cases for k: k0, k positive, k negative. After the dust settles, we find out that k positive is the interesting case. The details here, again, are worked out on page 202 of my notes. After the dust settles, we learn sine of n pi x over L with k is n squared pi squared over L squared. We'll do nicely. Aha. So great. That's what the spatial part of the product solution looks like. How about the temporal part? Now, you notice this time, I couldn't, like before with the heat equation, I just integrate the time solution. Easy peasy. You know, it's done. Now this time, I actually have to figure out the k in order to put it back in the time solution to find the time solution. It's a little bit more interesting. We have t prime prime plus k was n squared pi squared v squared over L squared. T equals to 0. Aha! Therefore, my time solutions are something like, you know, let's say a sub n cosine n pi v t over L plus b sub n sine of n pi v t over L. That's my nth temporal solution. And great, so my blank template then, put it together, what do you got? Something like y of xt equal to a sum, n equals 1 to infinity, of a sub n cosine n pi v t over L sine of n pi x over L plus b sub n sine of n pi v t over L sine of n pi x over L. Now all we have to do is figure out what the values are of a sub n and b sub n to fit my initial conditions. Which again brings us back to Fourier analysis for a general function, for a general f of x and g of x, right? So like, what happens when we look at y of x comma 0? What would it be? Put times 0, what term drops out? The b sub n, right? See, times 0 makes this piece gone, makes the cosine 1, and we just get a sub n